Let me start with something that happened this morning. You woke up, you made coffee, or someone made it for you. You poured it into a cup. It was hot. You set it down, got distracted, came back, and it was cold. That's it. That's the whole story. Hot coffee becomes cold coffee. Nobody is surprised by this. Nobody calls it remarkable. But I'm going to tell you that this ordinary, boring Tuesday morning event is the same phenomenon that will eventually end the universe. The same law that cooled your coffee is the reason stars die, the reason you age, the reason you remember the past and not the future, and the reason that everything is moving in one direction and cannot move in the other. The law is called the second law of thermodynamics, and it is, in my estimation, the most powerful and the most underappreciated idea in all of physics. Let's go through it properly. Slowly, the way you have to go through something real, what entropy actually is. First, we need to clear something up. Entropy is not disorder. I mean, it is, loosely speaking, but that word disorder carries too many human connotations. It suggests mess, chaos, things being wrong. Entropy is not about things being wrong. Entropy is about counting. Here is what entropy actually measures: the number of different microscopic arrangements that would look identical from the outside. Take a room, air molecules bouncing around, nitrogen, oxygen, a little carbon dioxide, all moving at different speeds in different directions. There are an almost incomprehensible number of ways those molecules could be arranged and still give you what you'd call a normal room with air in it. Same temperature, same pressure, breathable. From the outside, from the macroscopic perspective, all those arrangements look identical. They're all just normal room. Now imagine all the air in the room suddenly piling up into one corner, every molecule simultaneously in the same corner. This arrangement also looks like something from the outside. It looks like you're about to suffocate, and it's physically possible. Newton's laws don't prohibit it. The molecules could do that, but there's only one way for all the molecules to be crammed into one corner. There are an astronomical number of ways for them to be spread around the room. The spread out arrangements vastly, overwhelmingly, incomprehensibly outnumber the clumped up arrangement. So the air doesn't pile into a corner, not because some law forbids it. It doesn't pile into a corner because it would require a miracle of coincidence. Random motion almost never produces that outcome because almost all outcomes look like spread out air. The system wanders through possibilities and almost always ends up in one of the many spread out states rather than one of the vanishingly few clumped up states. That's entropy. High entropy means many possible microscopic arrangements. Low entropy means few. Systems naturally drift toward high entropy, not because they're pushed there, but because there are so many more high entropy states to land in. It's pure statistics, pure counting. And now your coffee. Hot coffee has fast-moving molecules concentrated in the cup. The air around it has slower molecules. This is a low entropy arrangement. There are relatively few ways to have that particular separation of fast and slow, hot here, cool there. As the coffee sits, fast molecules in the cup interact with slow molecules in the air. Energy spreads. The separation dissolves. The fast and slow molecules mix. You end up with a lukewarm cup and slightly warmer air. This state uniform temperature throughout has vastly more possible microscopic arrangements than the separated hot and cold state. Higher entropy. That's where the system ends up. That's where it always ends up. Nobody decreed this. The universe just counted its options and took the most likely path. The arrow nobody talks about. Here is the strange thing. Almost every fundamental law of physics works the same way forward and backward in time. Newton's laws, Maxwell's equations for electromagnetism, quantum mechanics, even general relativity. Run the equations forward, run them backward. They don't care. The mathematics is symmetric. Film a billiard ball rolling across a table and bouncing off the side. Now run the film backward. Does anything look wrong? No. The ball rolling backward obeys every law of motion just as well as the ball rolling forward. The laws don't have a preferred direction. Film your coffee cooling down. Now run that film backward. Hot coffee spontaneously appearing from cold coffee and cold air. Energy unspreading, concentrating itself back into the cup, warming it up from room temperature to scalding spontaneously. That looks wrong. Everyone knows immediately that it's backward. Why? Not because any fundamental law forbids it. At the level of individual molecules, nothing is stopping it. But the statistical improbability is so vast that we have never observed it happening, and we never will. The number of ways for energy to spontaneously reconcentrate is so tiny compared to the number of ways for it to stay spread out that we might as well call it impossible. This is where time gets its arrow. The direction of increasing entropy, the direction in which things spread out, mix, equilibrate, that is the direction we call the future. The direction of decreasing entropy, things unmixing, concentrating, organizing spontaneously, that is the direction we call the past. Time doesn't flow from past to future because the laws of physics demand it. Time flows from past to future because entropy increases in that direction, and entropy increases in that direction because there are so many more high entropy states than low entropy ones. The arrow of time is a statistical arrow, an arrow made of counting. And if you follow that arrow far enough, where does it lead? Why you age and don't unage. Look at your body. Look at what it takes to keep you running. You eat food. Food is a low entropy arrangement of matter, chemical energy stored in organized molecular structures. Your body breaks those structures apart, extracts the energy, uses it to do work, and expels the waste as heat and carbon dioxide. High entropy products. You are a machine that takes in low entropy and expels high entropy. The net entropy of the universe goes up every time you digest a meal. The work your body does with that energy includes maintaining itself, repairing cells, keeping concentration gradients intact, holding the extraordinary improbable structure of a living thing together against the constant pressure of entropy trying to dissolve it. And this is the thing, you are fighting entropy locally. You can do that. Nothing in the second law says local entropy can't decrease. It says total entropy, entropy of the whole system, you plus your environment must increase or stay the same. You can build order in yourself as long as you export more disorder to your surroundings, which you do constantly. You are a low entropy pocket maintained by a high entropy exhaust stream, but you can't fight it forever. Every year the maintenance becomes less perfect. Errors accumulate in DNA. Proteins misfold. Cellular machinery wears in ways that can't be fully repaired. You are not a closed loop. You are an open process, and the process degrades. The low entropy structure that is you becomes over time slightly higher entropy. The organization loosens. This is aging, not a disease, not a malfunction. The inevitable consequence of being a physical system in a universe that trends toward equilibrium. You will never unage. Not because medicine isn't good enough, though it isn't, but because reversing entropy locally requires pumping entropy somewhere else, and eventually you run out of room to pump it. The universe is finite in a certain sense, and entropy ultimately has nowhere to go but up. Why you remember the past and not the future? This one stops people cold when they really think about it. I want you to think about it. You have memories. You remember what you had for breakfast. You remember things that happened years ago. You do not remember tomorrow. You do not remember next week. Memory only runs in one direction. Why? The usual answer is because the past already happened and the future hasn't. But that's circular. It assumes the direction of time rather than explaining it. I want to give you the real answer. A memory is a record. Something that happened out there in the world, an event, a stimulus, caused a change in your brain. Neurons fired in patterns. Synapses strengthened. A physical trace was laid down. That trace is the memory. The event caused the record. Now, for a record to be reliable, causation has to run one way. The event causes the record, not the other way around. A footprint in the sand is a record of a foot because the foot came first and pressed the sand. The shape of the print carries information about the foot. If the sand had somehow shaped itself into a footprint and then a foot appeared, the print would tell you nothing reliable. It didn't record the foot, it preceded it. Records, memories, photographs, footprints, written history are low entropy arrangements that were caused by prior events in specific traceable ways. They exist because entropy was locally decreased in a structured manner by a particular cause. The direction from cause to record is the direction from lower entropy to higher entropy in the environment. It is the thermodynamic arrow. You remember the past because the past left records in the physical structure of your brain. The future hasn't left records yet, not because it doesn't exist, but because the low entropy causes that would create records of future events haven't happened yet from your reference frame. Memory is thermodynamics. The arrow of memory is the arrow of entropy. When you feel the asymmetry of time, the strange sensation that the past is fixed and the future is open, you are feeling entropy. You are feeling the statistical weight of an enormous number of microscopic arrangements pressing in one direction. Stars are fighting the same battle. The sun is not burning. That's the wrong word. Burning is a chemical process. The sun is fusing. Hydrogen nuclei in its core, protons, are being smashed together under enormous pressure and heat until they fuse into helium. This releases energy. Why does fusion release energy? Because helium is a lower energy, more stable arrangement than separated hydrogen nuclei. The protons want to be helium. The universe is nudging them toward a configuration that has more available microstates, more entropy, more equilibrium. Fusion is entropy happening at the nuclear scale. The energy released, the light and heat that make the sun shine, is the exhaust of that entropic process. The sun is exporting disorder into space in the form of photons, so that its core can maintain the conditions for fusion. It is doing exactly what you do when you eat and metabolize. Taking in low entropy, exporting high entropy, maintaining structure locally while increasing total entropy globally. But the sun has a finite supply of hydrogen. Every second, it converts about 600 million tons of hydrogen into helium. The hydrogen runs down. The supply is large. The sun has been doing this for 4.6 billion years and has about 5 billion years left. But it is finite. When the hydrogen in the core is exhausted, the sun can't maintain its structure against gravity. It will expand, cool, and eventually collapse into a white dwarf, a dense remnant slowly radiating its remaining heat into space, cooling over billions of years to nothing. More massive stars fight harder and lose faster. They fuse helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Iron is the end. Fusing iron costs energy rather than releasing it. When a massive star's core becomes iron, the energy source stops. The core collapses in less than a second, and the outer layers rebound in a supernova explosion. Brief, spectacular, and final. Every star in the universe is entropy happening on a cosmic scale, burning through its low entropy fuel, radiating high entropy heat, moving toward equilibrium. All of them, every single one. The heat death of the universe. Follow the logic all the way. Don't stop in the middle because it gets uncomfortable. Follow it. Stars burn out. Black holes form from collapsed massive stars and from dense galactic centers. Over extraordinary timescales, black holes grow by absorbing matter. But black holes aren't permanent either. Stephen Hawking showed, and this is a remarkable result, because it combines quantum mechanics with general relativity in a way that almost nothing else does, that black holes slowly emit radiation, not through any matter escaping, but through quantum effects at the event horizon. Hawking radiation. The radiation carries energy away from the black hole. The black hole loses mass. Over an almost incomprehensibly long time, far longer than the current age of the universe for any large black hole, it evaporates. It radiates itself away into low-energy photons, spreading its energy diffusely through space. What's left? Diffuse radiation, particles with almost no energy, space expanded to extraordinary scale, cold, homogeneous, no temperature gradients, no concentrations of energy, no low entropy pockets, no structures, no stars, no planets, no molecules, no atoms in any organized form, maximum entropy, thermodynamic equilibrium. This is called the heat death of the universe, and it is the inevitable endpoint of the second law applied to the entire cosmos, run forward to its final conclusion. No more gradients means no more work can be extracted. No work means no processes. No processes means nothing happens. Not ever again. The universe reaches a state of perfect, permanent, undifferentiated sameness, maximum entropy, complete equilibrium. Now, this is a very long time away. Current estimates put the final evaporation of the largest black holes at something like 10 to the power of 100 years from now. The current age of the universe is about 14 billion years, which is 10 to the power of 10. We are early. Absurdly early. We are living in what future physics, if there were any future physicists, which there won't be, would consider the very first moments, the structured low entropy beginning of things. But the direction is fixed. The arrow points one way. The heat death is where the arrow points. But why was entropy low to begin with? Here is the question that nobody asks enough, and which I think is actually the deepest question in physics. If the universe naturally trends toward high entropy, why was it ever low entropy? Why wasn't the universe born in a state of maximum entropy, a uniform fog of radiation going nowhere, doing nothing? Why did it start as a hot, dense, extraordinarily structured, extraordinarily low entropy state that then had room to expand and spread and differentiate and produce stars and galaxies and coffee cups and people? This is the real mystery. Not why entropy increases. That part is statistics, and statistics is clear. The mystery is the initial condition. Why was the entropy of the early universe so extraordinarily low? The honest answer is, we don't fully know. This is a live problem in cosmology. Some researchers think the answer lies in inflation, a period of rapid expansion in the very early universe that stretched space-time smooth and flat, and in doing so, created an unusually ordered gravitational starting state. Others think it requires a deeper understanding of quantum gravity. Others think the question of initial conditions may be unanswerable within physics, that it is simply the boundary condition of our universe, a given, not something physics can explain. What I can tell you is this. If the initial entropy had been higher, even a little, none of this would exist. No concentration of matter, no gravitational collapse, no stars, no complexity, no life. The extraordinarily low entropy of the early universe is, in a very direct physical sense, the reason you exist. You are a brief eddy of order in a universe trending irreversibly toward disorder. Your existence was made possible by the universe starting in an improbably special state, and you are spending that specialness, spending that initial low entropy, a little at a time every day, turning food into heat and structure into dissolution. We are all, in this sense, living on borrowed time, borrowed from the initial conditions of the universe. What entropy does to information. One more piece. I can't leave this out because it changes the picture entirely. In the 1940s, a man named Claude Shannon was working on communication theory, how to send messages reliably down noisy telephone lines. In doing so, he invented a mathematical theory of information, and when he wrote down the formula for information, it was identical, not similar, identical to the formula Boltzmann had written down for entropy 70 years earlier. Entropy and information are the same thing, or more precisely, they are two perspectives on the same mathematical object. High entropy means high uncertainty, many possible microscopic states, so knowing the macroscopic description tells you little about the microscopic details. Low entropy means low uncertainty, few possible states, so the macroscopic description pins down the microscopic state quite tightly. What this means is that when entropy increases, information is lost. The detailed microscopic description of the system, which molecules were where, moving how fast, gets smeared out. When your coffee cools, the information about exactly which molecules were in the hot state and which were in the cold air gets mixed and spread until it's practically irretrievable. The information isn't gone in an absolute sense. If you could track every molecule, it would still be there in the positions and velocities. But it becomes inaccessible, spread across degrees of freedom you can't observe. This connects to one of the deepest unsolved problems in physics, the black hole information paradox. When matter falls into a black hole, and the black hole evaporates via Hawking radiation, what happens to the information that was in the infalling matter? Hawking radiation appears to be completely random. It doesn't seem to carry information about what fell in. So where does the information go? Is it destroyed? Most physicists believe information cannot be destroyed. Quantum mechanics depends on it. But if information can't be destroyed and black holes evaporate, the information must somehow come out in the Hawking radiation, encoded in subtle correlations that look random but aren't. Proving this, understanding how, is one of the central challenges of quantum gravity. Entropy is information. The fate of information is the fate of entropy. And the fate of entropy is the fate of everything. Back to the cold coffee. So, you came back to your coffee, and it was cold. Here is what actually happened. The universe moved from a lower entropy state to a higher entropy state. The direction from that lower entropy state to the higher entropy state is the direction you call forward in time, and you know it was forward in time because you remember the coffee being hot and do not yet remember it being cold again, which it will never be unless you reheat it, which costs energy, which comes from some other low entropy source, which was itself made possible by the low entropy of the early universe, which is a mystery we haven't fully solved. Your coffee cooling is not a trivial event. It is a window. It is the second law being demonstrated in your kitchen at 9 in the morning. The same law that ends stars and will end the universe, happening right in front of you in a ceramic mug. The universe is not a machine running down from neglect. It is doing exactly what the statistics demand. It is following the most probable path. It started in an improbably ordered state, and it is moving, inevitably, toward the most probable state of all, which is uniform, featureless, empty equilibrium. Everything in between, stars, planets, oceans, biology, cities, history, art, science, everything you have ever known or cared about, is what happens on the way. We are structure. Temporary, improbable, entropy-defying structure. The universe made us by accident, from a low-entropy initial condition, through billions of years of gravitational collapse and nuclear fusion and chemical complexity. We exist in the window between the ordered beginning and the disordered end. We are what the universe looks like when entropy is partway through its journey. You cannot escape entropy. It is not coming for you like a predator. It already has you in the same sense that the laws of statistics already have you. You are participating in it every moment. Every thought you think, every calorie you burn, every word you speak heats the universe by a tiny, unmeasurable, real amount. You are spending entropy. You are part of the process. The question is not whether you can escape it. You can't. The question is what you do with the low entropy you've been given. What do you build with it? What order do you create locally? What structure do you make before the statistical tide comes in? This is not philosophy. This is thermodynamics. But it is thermodynamics that when you actually understand it, not just repeat the words, but feel what it means, changes the way you think about every hot cup of coffee you will ever hold. Drink it while it's hot.